In this video, I want to talk about prime and composite numbers. If you already understand prime and composite numbers, there's probably no need for you to watch this video. The chapter or the section should be just fine for you. A prime number is a number that has only two divisors or only two factors that are positive. We aren't concerned with anything that's negative for these. We're only dealing with natural numbers. So the numbers that you see in this box that are in the grid, 2, 3, 5, 7, 11, 13, and so on, these are considered prime numbers. A prime number has exactly two positive divisors, 1 and the number itself. So the only numbers that go into 7 evenly are 1 and 7. The only numbers that go into 19 evenly are 1 and 19, and so on. If a number has 2 and only 2 divisors, that number is prime. If a number has more than 2 divisors, or more than 2 factors, factors and divisors are synonyms. They mean the same thing. If a number has more than 2 factors or more than 2 divisors, that number is composite. Notice that the number 1 is a special case. It has a single factor itself. Therefore, it is not prime, and it's also not composite. How can we show that one of these numbers is composite? All we have to do is find a number that it can be divided by. So using our divisibility rules, we know that since 1,564 ends in an even number, that number is composite. And we know that since the digits of 2,781 add up to be 18, that means that 3 and also 9 divides 2,781. It too is a composite number. For a number like 1001, it can be trickier. One thing you can keep doing is checking. I want to show you how to check. To check if a number that you're not sure about immediately is composite or not, what you should do is, using your calculator, take the square root of the number. So we want to know what the square root of 1001 is. And so I'm going to move my calculator over here. And I'm going to find the square root of 1001. And I see that it's approximately, it's 31 and a bit. So I'm just going to round it to whatever the smallest number close to it is. So even though I would normally round this to 32, I'm just going to round this to 31. I need to check 1001 and see if any prime factors less than 31 divide it evenly. If any do, then it's not prime. If none do, then it is. So I need to check that list of prime numbers we saw a couple slides ago. Well, I can check 2 very simply. I know that 2 does not divide 1001. I also know that 3 doesn't, and I know that 5 doesn't divide that number. I know that because of my divisibility rules. So I'm going to check 7. That's my next prime number. So 1001 divided by 7 is 143. 143 times 7 is 1001. So since 7 does divide, should be 1001, does divide 1001, therefore I know 1001 is composite. So if 7 didn't divide, I would keep going. I would check 11, 13, 17, 19, 23, 29, and then finally 31 itself, which is prime. But as soon as I find one that divides it, I can stop. And 1001 is also actually divisible by 11, I believe. So there's more factors that would prove it's prime than just that. Here we have something that looks really complicated at first. We say, well, this is, prime times a prime times a prime times a prime times what's going to be an even number. And here's our rule. Any odd, so we have an odd times an odd number times an odd number is going to be an odd number. So 3 times 5 is 15, but also 5 times 7 is 35, 7 times 11 is 77. Any odd number times another odd number, your answer is going to be odd. Any even number times an odd number, your answer will be even. Any even number other than 2 is a composite number. This would be composite anyway because we have all of these numbers multiplied together. It's clearly composite. So yes, this is a composite number. When we look at what numbers multiplied together equal a composite number, we call that a factorization. And we're most interested in math with prime factorizations, a factorization that contains only prime numbers. That's the fundamental theorem of arithmetic. Every composite number can be written as a product of primes in only one way. And we always remember that order doesn't matter. So 2 times 3 times 5 is the same as 5 times 3 times 2. That's still just one way. But, so let's just look at that example. 2 times 3 times 5. 2 times 3 times 5 equals 30. There is no other combination of prime factors that equals 30. The only prime factors that equal 30 are 2, 3, and 5. We multiply those together. And again, it doesn't matter if we do 5 times 2 times 3, or 5 times 3 times 2, or 2 times 3 times 5. By convention, when we write a prime factorization, we put it in increasing order. So the best way to write this as an answer is like this, 2 times 3 times 5. We find prime factorizations by using factor trees. So here we have an example of two completed factor trees. One is for the number 84 and one is for the number 495. To start a factor tree, we just try to find two numbers that when multiplied together will equal the number whose prime factorization we're trying to figure out. And obviously we aren't going to include the number 1, because every number has 1 in itself as factors. Numbers other than that. Now if the number is prime, then that's all it will be. The prime factorization of 5 is 5. But here we see that 4 times 21 are 84. There are other combinations we could also use. 6 times 14 is 84. We could have used those also. It doesn't matter which factors we use, we'll always get the same answer at the end. So when we break this apart, we see that 4 is the same as 2 times 2, and 2 and 2 are both prime, so we stop there. And 21 is the same as 3 times 7, and 3 times 7 are both prime, so we stop there. So the prime factorization of 84 is going to be 2 squared times 3 times 7. Notice we always use exponents when we write prime factorizations, and again, the convention is we go from smallest to largest. Remember, these numbers are being multiplied together. A common mistake that people make is they think for some reason they are added, which they're not, they're multiplied. Over here on the right-hand side of your screen, they've done the same thing for 495. 495 is 5 times 99. And again, that's not the only way we could find it. We could also do this as 11 times 45. That also works. But this is one way. 5 is prime, so we stop there. 99's factors are 11 and 9. Again, not the only factors that exist. We could do 33 and 3 also, for example. 11 is prime, so we stop there. And then 9's prime factors are 3 and 3. So this is 3 times 5 times 11. We write that as 3 squared times 5 times 11. And if we check that in our calculator, we will see that we get 495. So let's check it on our calculator. 3 squared times 5 times 11. I should get 495, and I do. Again, the order you do this in doesn't matter. That's what this slide is showing. They started with 260. So they pretend two different people did a prime factorization of 260. One person, using probably divisibility rules, realized, oh, 260 is 26 times 10. And then 26 is 2 times 13. 10 is 2 times 5. So 260 is going to be 2 squared times 5 times 13. Another person said, well, 260 ends in 0, so that means it's divisible by 5. That's a divisibility rule. And 5 times 52 is 260. So we know 5 is prime. 52 is even, so it's going to be 2 times something. It's going to be 2 times 26. And 26 is even. So that's going to be 2 times 13, and 13 is prime. So they got their factors, and they would write the exact same thing as their answer. 2 squared times 5. This is a times, not a minus. Times 13. So it doesn't matter what factors you start with. Here we did 26 and 10. Here we did 5 and 52. We could have done 130 and 2 and gotten the same thing. We could have done 13 and 20 and gotten the same thing. It doesn't matter what factors we start with. What matters is that we keep working sort of down the tree until we get only prime factors. Once it's prime, we stop. I like to circle it when I get to a prime factor. That way, it's easy to forget to include one, especially when you have a long list of prime factors. It's easy to forget to include one. This is another way of doing it, which I personally don't like, but your book talks about it. You're free to do it this way if you want. I like using factor trees. And when I would teach this in school, I would teach this using factor trees also. Unless, obviously, if your curriculum is ever going to say, though, they have to know this form, then you have to teach a certain form. But factor trees are the most commonly used in my experience. Something else you might be asked to find is the number of positive divisors that a number has. Now, when it's asking this, it's asking not for the prime divisors, but just for how many there are. And so what we do in a case like this is we want to list the possible divisors. And so how well you do this depends on how well you remember multiplication facts. Right? So 24, we have 1 and 24. 2 and 12, 3 and 8, 4 and 6, and then you'll notice we be the same in reverse: 6 and 4, 8 and 3, 12 and 2, 24 and 1. We don't count them twice; we just count them once. So 24 has a total of 8 positive divisors. If you got a number you weren't sure about, you would then just check using either divisibility rules or your calculator to see if numbers are divisors. What you can do again is take its square root first. So the square root of 24 is going to be 4 point something. It's 4 and a bit. Since you're asked to find divisors, not just prime, you're going to check 24 by every number up to and including 4. And once you check them, you'll be able to tell them then just count. So you don't have to check every number up through 24. You just have to check every number up through the square root of the number. So if I wanted to find the number of divisors of 87, how many divisors does 87 have? I take the square root of 87, which is 9 point something, and all I have to do is I check 1 through 9. And using my divisibility rules, I see that divisors of 87 are 1 and 87. 8 plus 7 is 15, so 3 does divide into 87. I'm using my calculator off screen here just to quickly figure out what that is. That's 29. I know from divisibility rules that 4, 5, and 6 don't divide it. I'm going to check on 7 with using the calculator, and it does not. 8 does not, and 9 does not. So the number 87 has 4 divisors. So knowing this trick of taking the square root and just checking the divisors up to that number will have the amount of work you have to do. Or more than have it. I mean, it'll be much less than it would be otherwise. So rather than checking every possible number up to 87, all I have to do is check every possible number, every possible natural number up until 9. And remember, natural numbers are our counting numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. Divisors or factors are always natural numbers. We could also do a prime factorization and then work that way using our fundamental counting principle. And that can work for more complicated ones also sometimes. And that might work well for a more complicated problem like 1 million. So again, we could use the trick of take the square root of 1 million, which I'm doing off camera here. But the square root of 1,000,000 is 1,000. And I do not want, right, obviously, to figure out 1,000 different divisors. That's a lot of division to try. So instead, what I'm going to do is do first a prime factorization of 1 million. So 1 million is 1,000 times 1,000. It's good to include our commas. So we should always include commas for numbers more than 9,999. It's okay, usually, if you don't include them for numbers between 1,000 and 9,999. I should also add that when I draw on my screen in PowerPoint, it occasionally makes these artifacts. I don't know why. It happens on any computer I do it on. So ignore it when you see one of these straight horizontal lines. So 1,000 is 10 times 100. 10 is 2 times 5. 100 is 10 times 10. And each of those are going to be 2 times 5. And this 1,000 is going to be the exact same thing. Again, there's other ways we could have done this. We could have divided things by 25 or 500. You don't have to do it in this particular order, although I think this is a pretty quick order for this example. So my final digits on each stem of the tree are my prime factors. And you see I just have factors of 2 and factors of 5. So the prime factorization of 1 million that we found is 2 times 2 times 2 times 2 times 2 times 2. That's 1, 2, 3, 4, 5. We have 2 to the 6th times 5 to the 6th. And again, it's good to check this. I'm going to check this on my calculator. 2 to the 6th times 5 to the 6th. And I get 1 million. So all I need to find now are the number of factors that 2 to the 6th has and the number of factors that 5 to the 6th have. That answer is always going to be the exponent plus 1. Let me say that again. That answer is always going to be the exponent plus 1. So 2 to the 6th, the exponent is 6. So it has 6 plus 1 divisors. Why does it have 6 plus 1 divisors? That would be a good question to ask, and hopefully you're asking yourself that if you're not sure already. So 2 to the 6th has 6 plus 1 divisors because 2 to the 6th is this number. It's 2 times 2 times 2 times 2 times 2 times 2. And we remember, though, that every number also has 1 as a divisor. So 2 to the 6th has 7 divisors. If instead we had gotten 2 to the 8th, it would have 9 divisors. If we would have gotten 2 squared, it would have 3 divisors. If we would have gotten 2 to the 12th, it would have 13 divisors. 5 to the 6th, it's going to be the same thing. 5 to the 6th is 5 times 5 times 5 times 5 times 5 times 5 times 1. So again, 7 divisors. So we have 7 divisors for 2 to the 6th. We have 7 divisors for 5 to the 6th. Then we use our fundamental counting principles when we have choices. And we have a total of 7 times 7. 7 for this, 7 for this. We have a total of 49 divisors. So for a problem that is a small number, a smaller number, it can be quicker just to see what numbers divide into it, often by using our square root trick. For a larger number, it's often going to be quicker to find its prime factorization first. You might also be asked to do a prime factorization or find the number of divisors for a number that is expressed with an exponent. So this number is 210 times itself 10 times, which I'm not going to write. To find the prime factorization of 210 to the 10th, what we do is we just find the prime factorization of 210. So we're going to find the prime factorization of 210. That's 21 times 10. Notice how divisibility rules make this so much quicker for us. Any number that ends in 0 is divisible by 10. 21s is 7 times 3. 10 is 2 times 5. So the prime factorization of 210 is going to be 2 times 3 times 5 times 7. And then we're still taking that to the 10th power. So we have 10 of these, 10 of these, 10 of these, and 10 of these. And that works out, in other words, we have 2 to the 10th times 3 to the 10th times 5 to the 10th times 7 to the 10th. And then we figure out each of these. 2 to the 10th has how many divisors? Well, its exponent is 10, so 10 plus 1 is 11. 3 to the 10th, same thing. 5 to the 10th, same thing. 7 to the 10th, same thing. So we have 11 times 11 times 11 times 11, which is 11 to the 4th power. And when we find 11 to the 4th power in our calculators, we see that this number, 210 to the 10th power, has 14,641 divisors. Now, this is a good case of why it's important to know math beyond just using a calculator, because 210 to the 10th isn't displayed in your calculator using regular notation anyway. It ends up showing up in scientific notation. Still, other numbers you might work with are actually too big to be displayed in the calculator at all. But even with a very large number, using these rules, we can still answer questions involving how many divisors it has, or in a case like this, we can still find a prime factorization of it even. And we've already talked about this, but I'll remember again. To determine if a number is prime, you check divisibility by prime numbers less than the given number But again, this is that makes sense. Their explain is a little trickier than I did. I think it's more math, I guess a math theorem or a math proof. It's the same idea. If you were asked for 397, the first thing you would do, is it prime or composite, is take its square root using your calculator. There is a way to find square roots by hand, but it's literally never taught anymore because it's really time intensive. The square root of 397 is 19 and a bit. It is 19.92, but it keeps going on. It's an irrational number. It doesn't end, but it's 19 and a bit. We check it by the prime numbers up to 19. So we check it by numbers 2, 3, 5, 7. And if any of these prime factors divide 397, then we know it is composite. If none of them divide 397, we know it's prime. So right away we know that 2 doesn't divide it because it's not even. We know 3 doesn't divide it because the sum of its digits doesn't equal a multiple of 3. And we know that 5 doesn't divide it because it doesn't end in 0 or 5. Using my calculator, I'll check if 7 divides it, and it does not. I'll check if 11 divides it, and it does not. I'll check it if 13 divides it. It does not. I'll check if 17 divides it. It does not. We know that 19 doesn't divide it. Because the square root is almost 20. So 19 clearly doesn't divide it. But I'll check it anyway just to make sure. So 397 divided by 19 is 20.89. So 397 is a prime number because none of these prime factors divide it. We'll do the same thing for 91. So the first thing to do is estimate its square root. And you could estimate a square root very easily. You don't even need a calculator to estimate most of them. We know, hopefully, that the square root of 81 is 9. And if you remember high school algebra, you know that the square root of 81 is actually positive 9 and negative 9. We're only interested in positive square roots in this class. And we know the square root of 100 is 10. So the square root of 91 has to be between 9 and 10. So that means I need to check. So that means I'm going to say it's approximately 9 point something. Doesn't matter point what. I check for prime factors up to this number. So the prime factors up to or equal to 9 would be 2, 3, 5, and 7. We know that it's not 2 because because it doesn't end in, it's not an even number. It doesn't end in 0, 2, 4, 6, or 8. We know it's not 3 because 9 plus 1 does not equal a multiple of 3. We know it's not 5 because it doesn't end in 0 or 5. So we'll check 91 divided by 7. And 91 divided by 7 is 13. So 7 works. 91 divided by 7 is 13. So 91 is a composite number. If we were finding its prime factorization, it has just one way to find it. It's going to be 7 times 13. Or 13 times 7. It is composite. Another way to find primes, and if you teach middle school eventually, you might use this with your students. It's called the sieve of Eratosthenes. Eratosthenes was a Greek mathematician. We do this using a hundreds chart. There's actually all sorts of math you can do using a hundreds chart well beyond, kindergarten, first grade when we're learning to count. And so what we do is look at a hundreds chart and we cross out 1 because 1 isn't prime. 2 is prime, so we're going to circle that. And then I'm going to cross out all of the multiples of 2, which is going to take me a while. So I'm going to pause this while I do this. This is already a super long video. So all my 2's are crossed out. That means my next number is prime. So 3 is prime. So now I'm going to do the same thing. I'm going to cross out all the multiples of 3. If something was already crossed out, like 6 is also a multiple of 2, I'm just going to skip it. Sometimes we have students use different colors and stuff like that. That's fine. You could do that. But in the interest of time, I'm just going to cross out multiples of 3. So I'll start with 9. I'll go on to 15, and then I'll keep going and come back to our video. So I've crossed out all the multiples of 3. The next non-crossed out number in my sieve is number 5. And so now I'll go through and I'll cross out all the multiples of 5, which are going to be every number that ends in 5. I've already crossed out every number that ends in 0. I then go on to my next number. That's 7. So now I'm going to cross out all the multiples of 7, which the first one I'm going to get to is actually 49. And I'll do that and come back. I've crossed out my multiples of 7. Now my next number that isn't crossed out is 11. That means 11 is prime. And so that means I'm going to cross out any multiples of 11 that aren't already crossed out. And you'll notice my multiples of 11 are the diagonal going down from 11 here. So 22, 33, 44, 55, and those are already all crossed out. I then go to 13. And so now I'm going to cross out multiples of 13. So I see that some of them are already crossed out, but I'll check and see if there's any more I need to add to that list of crossed out ones. So I'll do the same thing now with 17. I think my multiples of 17 have already been crossed out. I have 34 crossed out. 51 is crossed out. 68 is crossed out. 85 is crossed out. So all my multiples of 17 are crossed out. I'll do the same thing going through with 19 and 23 and 29 and 31, and then I'll check back in. So the rest of the chart is going to be really quick for us because we've stopped at 100. So, for example, for 29, every double of a number is going to be that number times 2, which means that number is even, which means it's not prime. The only even prime number is the number 2. So 29 times 2 is 58, and 58 plus 29, so any number times 3 is going to be an odd number. 58 plus 29 is 87. But I already have 87 crossed out. So same thing for 31. 31 times 2 is 62, which we know is composite. But 31 times 3 is 93. I've already crossed that out. 37 times 2 is 74, which we know is composite because it's even. 37 times 3 is already 111. So everything else here is going to be actually prime. So 41 is prime, 43 is prime, 47 is prime, 53 is prime, 59 is, 61 is, 67 is, 71 is, 73 is, 79 is, 83 is, 89 is, and 97 is. So once we get to the point where we would have to triple a number to see what its multiple is, we're already beyond our chart. So here we have the prime numbers that are less than 100. This is the sieve of Eratosthenes. It's always a way to find out what numbers are prime. And here's how it looks like in your textbook, where they were using different colors and things to work with it, which, yeah, that's all them. So that's how it looks for them. So hopefully this makes sense for you for prime and composite numbers. You need to be able to distinguish what they are, and you need to be able to use prime factorization. And you should be able to determine if a number is prime or composite. I know this video was kind of lengthy. I apologize for that, but I hope it helps you if you need the help. Good luck as you move forward.